For decades, the idea of journeying to other stars has captivated the human imagination. It fuels countless stories, blockbuster movies, and late-night debates among science enthusiasts. We've managed to send robotic emissaries like Voyager 1 and 2 out of our solar system, but the leap to sending humans to another star system? That's a cosmic chasm of a difference. The sheer distances involved are so mind-boggling that even our fastest spacecraft today would be on a multi-generational voyage, tens of thousands of years just to reach our nearest stellar neighbor, Proxima Centauri. So, what's the holdup? What are the fundamental scientific and technological barriers that keep interstellar travel firmly in the realm of dreams? In this video, we're going to delve into the 5 most significant hurdles that stand between us and the stars. We'll explore the tyranny of distance and the speed of light, the almost unimaginable energy requirements, the need for a starship that can withstand the harsh realities of deep space, the monumental challenge of keeping our astronauts alive and thriving for potentially centuries, and finally, the perplexing question of how we even communicate across light years of emptiness. Buckle up, fellow cosmic dreamers, because we're about to confront the top 5 biggest obstacles to star hopping. 1. Distance and speed limits, the unyielding light year. The number 1 colossal obstacle to interstellar travel is, without a doubt, the sheer, unfathomable distances between stars. Space isn't just big, it's an almost incomprehensible void. Our closest stellar neighbor, the Alpha Centauri system, is roughly 4.37 light-years away. Now, even if we could somehow achieve the ultimate speed limit, the speed of light, and spoiler alert, current physics tells us we can't, it would still take over 4 years just to make the one-way trip. But consider our current reality. Our fastest spacecraft, Voyager 1, is cruising at a respectable 38,000 miles per hour, or about 17 kilometers per second. At that pace, reaching Alpha Centauri would take over 70,000 years. Think about that timescale. Civilizations have risen and fallen within that span. Clearly, if humanity is serious about becoming an interstellar species, we need a radical breakthrough in propulsion, something far beyond anything we've conceived, perhaps even something that bends our current understanding of physics. But the brilliant minds in space science are indeed cooking up some tantalizing theoretical possibilities. Nuclear fusion rockets harnessing the power of miniature suns. Imagine rockets powered by the same atomic process that fuels our sun. Fusion could generate immense thrust, potentially propelling us to significant fractions of the speed of light. The catch? Achieving controlled, sustained fusion here on Earth is still a monumental engineering challenge. Mastering it within the confines of a rocket engine? That's a whole new level of complexity. It makes you wonder if we're trying to capture lightning in a bottle, but on an interstellar scale. Antimatter engines, science fiction, or future reality. Antimatter, the mirror image of ordinary matter, releases an unbelievable amount of energy when it annihilates with its counterpart. Matter meets antimatter? Instant, pure energy. The problem? Antimatter is the most expensive substance to produce in the universe, and storing it safely? That's akin to trying to contain a fundamental force of nature. It's the ultimate high-risk, high-reward fuel source. Laser-powered light sails, riding the cosmic wind. This concept is truly captivating. Picture a spacecraft equipped with a gigantic, incredibly thin sail, propelled through space by powerful lasers fired from Earth. Like surfing on beams of pure light. This is the core idea behind projects like Breakthrough Starshot, which aims to send tiny probes to Alpha Centauri. It's a beautiful vision, a testament to our ingenuity, but scaling this up to transport humans across interstellar distances presents immense engineering hurdles. These are all incredibly ambitious and potentially revolutionary ideas. But let's be honest, we are currently light years away from having a reliable, warp-drive-ready interstellar vehicle capable of transporting humans. Yet, every grand endeavor, every journey to the unknown, begins with a single spark of an idea. 2. Energy needs, fueling a journey across light years. Traveling to another star demands an almost ludicrous amount of energy. To reach even a fraction of the speed of light, say, 10%, 0.1 c, A starship would require more energy than all the power plants on Earth combined could produce over several years. Just to accelerate a hypothetical 1,000-ton starship to 10% of light speed would necessitate around 100 quadrillion joules of energy per second for an extended period. That's far beyond our current global energy output. Where could such an immense power source possibly come from? Space science visionaries have some intriguing concepts. Nuclear power, unleashing atomic potential, nuclear fission, and even more promisingly, nuclear fusion reactions could unlock colossal amounts of energy in space. But we're talking about reactors far more advanced than anything we have today. Think science fiction levels of miniaturization and power generation. It raises the question of safety and the long-term sustainability of such power sources in the unforgiving environment of deep space. B. Antimatter, the ultimate energy density. Once more, antimatter emerges as a potential solution. In theory, just a few grams of antimatter could fuel an entire interstellar voyage. But the monumental challenges of production and safe storage remain significant roadblocks. It's a tantalizing prospect, but the practicalities are still firmly in the realm of theoretical physics. Solar or laser power beaming, tapping into external energy sources. Imagine harnessing the sun's limitless energy with massive solar arrays in space, or perhaps blasting giant, focused lasers at our starship to provide continuous thrust without the need to carry vast amounts of fuel. Ingenious? Absolutely. But the engineering complexities of maintaining such a system over interstellar distances are staggering. It makes you wonder about the vulnerability of such a system to cosmic events or even intentional interference. Until we can fundamentally crack the energy problem, interstellar travel will remain a distant aspiration, a beautiful dream just beyond our grasp. 3. Starship durability, navigating the cosmic shooting gallery. Let's assume, for a moment, that we've solved the propulsion and energy puzzles. What's the next major headache? The reality is, space is a dangerous environment. At the incredibly high speeds required for interstellar travel, even microscopic particles of dust can become catastrophic hazards. Picture our starship cruising at, say, 10% of the speed of light. That's a staggering 67 million miles per hour. If it were to collide with even a grain of sand at that velocity, the impact would be akin to a powerful explosion. Larger objects like asteroids or even discarded space debris, that would spell utter disaster. It's like trying to navigate a cosmic shooting gallery at warp speed. So, how do we armor our interstellar vessel for this cosmic demolition derby? Brilliant scientists are exploring some fascinating defense mechanisms. The advanced shielding, a robust outer layer, a thick, multi-layered protective shield could potentially absorb impacts from smaller debris. Think of it as building incredibly strong body armor for our starship. However, armor adds significant weight, which in turn makes acceleration even more challenging. It's a delicate balancing act between protection and performance. Electromagnetic deflectors, creating a force field. Some propose using powerful electromagnetic fields to deflect charged particles and smaller debris before they even make contact with the ship. It sounds like something straight out of science fiction, but the underlying physics are sound. The challenge lies in generating and maintaining such powerful fields over vast distances and long durations. Autonomous AI guidance, the ultimate cosmic autopilot. Imagine a highly advanced artificial intelligence system constantly scanning the space ahead, detecting even the smallest pieces of debris, and making instantaneous course corrections to avoid them. A cosmic autopilot with lightning-fast reflexes. This raises fascinating questions about the level of autonomy we would entrust to such a system and the potential for unforeseen circumstances. Even with these innovative ideas, ensuring the structural integrity of a starship for the decades, or even centuries, required for interstellar travel is a problem we haven't even begun to fully comprehend, let alone solve. 4. Human survival, life support for generations. Interstellar travel isn't just about building a fast and durable ship. If we're sending humans on these epic voyages, we need to keep them alive and healthy for potentially generations. This opens up a whole new realm of complex challenges. Food and water, the closed-loop ecosystem. Forget packing enough rations for a multi-century journey. We need to develop completely closed-loop, self-sustaining life support systems. Think massive, on-board hydroponic farms growing fresh food and incredibly efficient closed-cycle water recycling systems, far beyond what we currently have on the International Space Station, all operating autonomously for generations. It's about creating a miniature, self-contained Earth within the confines of a starship. Irradiation exposure, the invisible threat. Deep space is filled with dangerous radiation from cosmic rays and solar flares. Long-term exposure can lead to severe health issues like cancer, organ damage, and even genetic mutations. Future starships would require robust radiation shielding, but again, heavy shielding adds weight and slows us down, another intricate puzzle for scientists. It forces us to consider the fundamental limits of human biology in the face of the harsh cosmic environment. Psychological and social challenges, the human element. Now, things get really interesting and perhaps deeply personal. Imagine being born on a starship, knowing you might never set foot on an actual planet. Your grandchildren might be the first to see another star system up close. How does that impact the human psyche? Long-duration space missions will require careful consideration of social dynamics, multi-generational crews, perhaps even advanced AI companions to combat loneliness. And then there's the intriguing possibility of cryosleep and hibernation, pausing human biology. What if we could simply put our astronauts into a state of suspended animation? In cryosleep, they wouldn't need food, water, or social interaction for decades. Problem solved, right? Not so fast. Human hibernation, in the science fiction sense, isn't really a reality yet. We don't fully understand how to safely pause human biological functions for extended periods, let alone reliably restart them without adverse effects. It's a tantalizing prospect, but the complexities of human biology are proving to be a significant hurdle. Cracking the human survival puzzle for interstellar voyages might be an even greater challenge than figuring out how to propel ourselves across the stars. But humanity is nothing if not adaptable. Perhaps, by the time we're ready to venture to other solar systems, we will have evolved in ways we can't even imagine today. 5. Communication challenges lost in translation across light years. Alright, the final major hurdle, communication. Let's say we successfully send humans, or incredibly advanced probes, to another star system. How do we stay in touch? How do we receive updates? How do they call home? Prepare for some serious cosmic lag. Radio waves, the current backbone of our space communication, travel at the speed of light, which, as we've established, sounds incredibly fast until you're dealing with interstellar distances. Even with a perfect, unimpeded signal, a message to Alpha Centauri takes a staggering 4.37 years to arrive. A round trip? Nearly 9 years. Imagine waiting almost a decade just to ask, "Hey, how's it going?" and get a reply. Think about that next time your internet is slow. So, how do we bridge this immense cosmic communication gap? Let's brainstorm some potential solutions. Laser-based communication, supercharged space fiber optics. Lasers can transmit data faster and more efficiently than radio waves. Think of it as supercharged fiber optics in space. The challenge lies in maintaining incredibly precise alignment over light years of distance. Quantum entanglement, the realm of spooky action. Now we're venturing into the truly mind-bending world of quantum physics. In theory, quantum entanglement might allow for instantaneous communication, regardless of the distance separating the entangled particles. Einstein called it spooky action at a distance. But we are currently light years away from turning this theoretical concept into a practical messaging system. Quantum texting? That's still firmly in the realm of science fiction. Autonomous AI, reducing the need for constant contact. Perhaps the solution isn't faster communication, but less communication. Instead of constantly relying on instructions from Earth, interstellar probes, or even human colonies would need highly advanced, truly autonomous artificial intelligence to make decisions independently. Think of sending out self-reliant robotic explorers into the cosmos. This raises profound questions about the level of trust we would place in such AI and the potential for unforeseen outcomes. The immense communication delays inherent in interstellar travel mean that any travelers would have to be incredibly self-sufficient, capable of solving problems and making critical decisions without waiting years for input from Earth. Okay, let's face facts. Interstellar travel, as we envision it today, remains firmly beyond our current capabilities. But that doesn't mean it's an impossibility forever. Humanity has always been a species of explorers, of dreamers, and of relentless problem solvers. With continued breakthroughs in propulsion, energy generation, starship durability, life support, and communication, someday, perhaps sooner than we think, we might just reach for those distant stars. Scientists are already tackling these monumental challenges head-on. Projects like Breakthrough Starshot are pushing the boundaries of laser propulsion, and NASA is actively researching advanced nuclear-powered spacecraft. The wheels of innovation are turning. Could we witness interstellar travel in our lifetimes? Realistically, probably not in the way we see in the movies. But in the next 100 to 200 years? Perhaps. Just perhaps. And think about how dramatically the world has changed in the last 2 centuries. No cars, no airplanes, no internet. Imagine the possibilities that the next 200 years could unlock. One thing is certain. If humanity truly desires to explore beyond our solar system, we have an immense amount of work ahead of us. But every journey, no matter how vast, begins with a single step, or maybe, in this case, a powerful rocket launch. Keep dreaming, keep exploring, and keep pushing the limits of what we believe is possible. Because the ultimate future of humanity just might lie among the stars. Thank you for joining me on this journey into the challenges of interstellar travel. If you found this exploration thought-provoking, please like this video and subscribe for more deep dives into the fascinating world of science and space.